Yeah, my name is Wooseok Byun from Chungnam National University in South Korea. And before we get into it, I want to ask your understanding that I stand here on behalf of my advisor, Professor Ji-Hoon Kim, due to his health problem. Today, I will talk about the fast visual target identification for low-cost BCI speller. This is outline of this presentation. First of all, I will talk about what is the brain-computer interface and our research goal, and then I will introduce our developed wearable BCI device, and to improve this device, the proposed target identification algorithm will be discussed. And finally, I will shortly introduce our further work for the hardware design. So let's start with what is the brain-computer interface. BCI is emerging communication channel for humans. So these are various BCI applications, and physically or mentally disabled people may often experience inconvenience. For those, the BCI technology can help them by connecting their intentions with the medical equipment. This can be classified as invasive or non-invasive depending on the surgical operation. However, among various applications, BCI speller are especially valuable for the patients with paralysis to communicate with other people. Currently, EEG is the most popular method of implementing the BCI speller system because it has non-invasiveness and simple operation and relatively low cost compared to the other method. So now I'd like to talk about the concept of BCI in this research. This BCI system uses visual stimulus. From the onset of this visual stimulus, the brain response will be generated, and we can measure this response through the electrode on the scalp. We are calling this brain signal as the visual evoked potential, shortly VEP. If the visual target flickers with specific frequency, in this case we are calling this brain response as steady-state visual evoked potential. This response contains the frequency information of the visual target. Then BCI system will perform the signal processing algorithms and then reveals what target the person is now looking at. Then how BCI system can identify the frequency information contained in SSVEP signal. The left graph answers for it. Unlike transient VEP, the SSVEP contains the target frequency and its harmonic components in the frequency domain. The BCI system can identify the target using predefined target to frequency mapping information. Finally, BCI system can display the identified target on the monitor. So this is our research goal. In previous BCI speller system, it has many electrodes on the head, and it is hard to wear, and it has long preparation time. But above all things, an expensive computing device like desktop PC makes it difficult to use. So we wanted to develop the wearable BCI device without extra computing resources. It supports on-device EEG signal processing. Under the aforementioned research goal, we previously developed the wearable BCI device. We achieved the behind-the-ear type wearable BCI device, but still the signal processing should be performed on the external desktop PC. We used the single-channel SSVEP and the raw data transmission through the through the Bluetooth. And the host PC receives the SSVEP raw data, and it runs the target identification software. The device consists of a 24-bit resolution ADC chip for performance evaluation. As you can see, the printed circuit board has small form factor to be compared with coin. We can attach it behind the ear like this. And this device has institutional review board approval in South Korea. This previously developed device can compare with the commercial products. It has a small size with low power and very comfortable to use, and it has high performance in terms of low noise and high resolution for the SSVEP sampling. But we are not satisfied for the requirement of a powerful computing PC. So now we can declare the improvement direction for the prototype device. There are 3 points to be improved. First, not enough signal-to-noise ratio, that is poor SSVP quality at behind-the-ear position, and the second, not enough computing power. It requires external computing device. And the third, not enough communication speed. These 3 points can be improved by our proposed solution. We moved the electrode to the back of the head, and we proposed the target identification algorithm while maintaining the BCI speller performance. And we reduced the signal processing time, especially the timing-dependent procedures. So we listed up the 3 conventional target identification algorithms to select the baseline algorithm for this research. The first candidate is power spectral density analysis. It works for the only single channel SSVP by the simple operations such as fast Fourier transform and finding the maximum index. Although it has simple operations, currently it is not so popular due to the weak performance for the low SNR SSVP signal. And the second candidate is Canonical Correlation Analysis, shortly CCA. There are many variations for the CCA, so we are calling the original CCA as standard CCA. It finds correlation between EEG signal and reference sinusoidal signal, which consists of a sine and cosine for the several harmonic components of the target frequency. We should compute this algorithm for each target frequencies, and after that, the frequency which has maximum correlation can be revealed as the target the person is now looking at. As you can see in the left picture, the CCA algorithm has many matrix operations. There is eigenvalue decomposition step, but it can be ignored with the system uses only single channel, like this research. The last candidate for the baseline algorithm is combination CCA. Compared to the standard CCA, it has additional training data set for the specific subject and has more accurate classification performance. It has not only the huge data sets compared to the standard CCA, but also has more computational complexity. So when we compare these 3 candidate algorithms for the single channel SSVP, the accuracy performance and the processing time will be like this. As you can see in the top of the right corner, the combination CCA has the highest accuracy and longest processing time compared to others. And there is another performance metric, ITR. It is widely used performance metric for the BCI speller system. Even though the ITR performance of the combination CCA degrades according to the recording times, it is always higher than other 2. So in this research, we selected the combination CCA for the baseline algorithm. The high computational complexity problem can be solved with our proposed optimization methods. So the name of our proposed target identification algorithm is CCA-LITE. We can take this algorithm by applying the 2 optimization methods into the combination CCA. The first optimization method is the signal binarization. It is really simple. The signal binarization maps the amplitude of SSVP to +1 or -1. Before applying the signal binarization, the combination CCA deals with multi-bit EEG or multi-bit reference sinusoidal signal. Then these cause the high computational complexity and high memory requirement. But with the signal binarization, we can solve this. The second optimization method is on-the-fly covariance calculation. This equation represents the mathematical definition and its expanded form. In the real-time signal processing point of view, the system should wait for the complete of expectation of X and the expectation of Y. But what if the multiplication of each expectation is negligible? Then we can ignore the calculation and we don't need to wait for it. We verified it for the SSVEP dataset, and the two terms have significant amplitude difference. And this optimization method didn't make the accuracy loss. By the on-the-fly covariance, the BCI splitter system performs the covariance matrix calculation while the SSVEP is on still recording. It improves the communication speed significantly. We used the low-power MCU platform, which consists of a Cortex M3 and with the several memories. And we used open-source SSVEP dataset for the whole experiments. From now on, I'd like to show you our experimental results. This slide shows the effect of signal binarization on the SSVEP according to its signal length. We can see the peak frequency error between the original SSVEP and the binarized SSVEP. As you can see, the 1.5 second SSVEP has the best quality with short recording time and negligible frequency error. This signal binarization can be applied to 3 data sets in the combination CCA. We found that the type 3 has a high accuracy with small memory requirement because the training data and the reference data should be pre-stored in the memory. And the signal binarization for these 2 data sets can reduce the memory requirement. This is the accuracy performance for the aforementioned algorithms. The proposed CCA-LITE has similar accuracy compared to the combination CCA with negligible accuracy loss. And while maintaining this accuracy, the proposed algorithm can reduce the target selection time, which is the time after the end of a recording, by 93%, and it can improve the ITR information transfer rate by 23%. We profiled the software performance on Cortex M3. For the memory footprint, the signal binarization becomes the important role to reduce the memory requirement by 92%. And the pure signal processing time on Cortex M3 can be reduced by 47% for the CCA-LITE. This is the last experimental results. This figure represents the overall BCI splitter system performance in terms of communication speed. In this research, the minimum gauge shift time is fixed as 500 milliseconds according to the previously reported works. By the proposed algorithm, the time for a single target identification can be reduced by 22%, and it means that the signal processing will be obviously done before the end of a 500 millisecond gauge shift time. Now, I'd like to introduce our ongoing work. We are going to improve the classification accuracy significantly using 8-channel SSVEP. It makes a huge increase of computational complexity, and the additional huge matrix operations such as the QR decomposition and inverse matrix, covariance matrix, or matrix multiplications should be performed on the wearable device. So we designed the system on chip with highly reusable 8x8 QR decomposition for the hardware accelerator. This engine has a strong foundation of a systolic architecture, and to supply various matrix operations at the same hardware, the processing elements are configurable. Compared to the same processing on software, the QR decomposition engine has high throughput and reduced memory access and low power consumption. For the analog front end, we used a high resolution ADC chip, but it will be integrated on a single chip. And thank you very much for ARM's design start support. This SoC runs with the Cortex M3 design start kit. Let me conclude this talk. There were 3 points in this presentation. We designed the low-cost wearable BCI system for the patients with paralysis, and the proposed algorithm shows significant improvement in terms of target selection time reduction by 93% and the information transfer rate improvement by 23%, finally total performance improvement by 22%. We showed the further work of a SoC design with hardware accelerator for the high accuracy. Thank you for your attention.
Any questions?
Sorry, this is somewhat irrelevant perhaps, but what do these electrodes actually measure?
It's a dry electrode, but I don't know exactly what the electrode we used.
So you've been playing with EEG data. How much does the computational burden increase if you have LFP data? Have you guys gotten a handle on that?
Pardon me?
If you use LFP data, local field potentials, do you know how much the computational burden increases by?
So I don't know exactly, but this data can be computed on the Cortex-M3 in the real-time processing. So its processing burden is not so significantly.
I have a question.
Yes.
So it looks like your device has 8 electrodes, which seems like less than one of those caps. So the effort for the user, is it more difficult to make things happen, or is it comparable effort, mental effort?
The electrode, the number of electrode is increased to 1 to 8 channel, but this 8 channel is location is on the occipital lobe. So it's not so. It may be comfortable to users. Yes.
Okay. Other questions?
If it wasn't visual, would you move it to a different location, you think? If the information input wasn't visual, would you move it to a different position on the head?
No, we use the electrode on the only occipital regions.
Anything else? Okay, thank you.
Thank you.